Hey guys, Justin here, and welcome to our 6th example video following our course on abstract algebra. Now, today's example video is going to be focusing on some more general results involving groups. So now that my introduction is out of the way, let's go ahead and get into the first example. So for this first example, we want to prove that G is abelian if and only if, for all A and B in G, we have that AB inverse is equal to A inverse B inverse. So to start this proof, let's do what feels most natural and start with the forward direction. So for the forward direction, we are going to be supposing that G is abelian. So I'll go ahead and write that. Suppose that G is abelian. And what we want to show is that for all A and B in G, we have that AB inverse is equal to A inverse B inverse. So to do this, I'm going to be using a relatively standard proof that we actually proved in the corresponding lecture video to this example video, and that is, in general, that AB inverse is equal to B inverse A inverse. Great. And so now that we have that frame of reference in mind, let's go ahead and get into our proof here. So to begin our proof, I want us to consider the following. So we want to consider AB, and that will be times B inverse A inverse. Great. So we can see right away we will have a cancellation of our B and our B inverse there in the middle, so that will leave us with A and the identity element and A inverse, but anything times the identity element is just the identity element, so that will give us A and A inverse, but A times its inverse will also give us the identity element. Great. So what have I proven here? Well, I've proven that AB inverse is equal to B inverse times A inverse. And it looks like I forgot to say that A and B are in G, so let me just put that right up here. Great. So now we're going to use the fact that G is abelian, and because it's abelian, that means that B inverse times A inverse is equal to A inverse times B inverse. Great. But if B inverse times A inverse is equal to A inverse times B inverse, that means that A B inverse must be equal to A inverse B inverse. But that is exactly what we wanted to prove for this forward direction. Great. So now let's go ahead and get into the reverse direction. So for the reverse direction, we want to prove exactly what we've just shown here, and that is to suppose that for all A and B, which are in our group G, that AB inverse is equal to A inverse and B inverse. But we can write that a different way, and that is that A times B times A inverse B inverse is equal to the identity element E. Now what we're going to do from here is multiply from the right by BA. So I'll go ahead and write that out. We're going to multiply from the right by BA. And so once we do that, on the left-hand side, we will have AB times A inverse B inverse, and then we will have from the right BA. And then since we're multiplying into the identity element on the right-hand side of our equation, we'll just be left with BA here. But we can see that these two B's are going to cancel. And once we cancel out our B with our B inverse there, we will be left with A times B times A inverse, and we will get an identity from that B and B inverse, and then we will have an A on the right-hand side there, and that will still be equal to B times A. Now we can get rid of that identity element, and that will give us A times B times A inverse times A. And once again, we have cancellation here with our A inverse and A, and that will be equal to B times A. Now I'm going to skip writing that goes to the identity because I think you guys probably know that by now, so that will leave us with A times B is equal to B times A. But that's actually all we wanted to prove, as we started with two arbitrary elements from G, A and B, and we showed that they commute here. Great. So that finishes this proof off, so let's go ahead and get into the next proof. So for the next proof, we want to suppose that G is a group of order 6, which contains 7 and 19, where the operation is multiplication modulo 36. We want to list all elements of G. So to do this, we're going to do what feels very natural, and we're just going to combine these elements using multiplication modulo 6 until we can generate 6 elements for the group. So let's go ahead and start out with the easiest one probably, and that is 7 times 7. Well, 7 times 7 is equal to 49, but 49 is exactly 13 more than 36, so that gives us our first additional element there. So now we have 7, 13, and 19. So in the same vein, let's go ahead and check 19 times 19. Well, 19 times 19 is equal to 361, which is exactly one more than 36 times 10, so that gives us our second element generated there, and that will be 1, which will also be the identity. Great. So now we have 4 elements, so let's find the last two. So let's try 7 times 19 first. Well, what is 7 times 19? Well, 7 times 19 is 133. And 133 is exactly 25 more than 36 times 3. So that gives us our fifth element, which is 25. Great. Now for our last element, we are going to use that 25 and multiply it by 7. And when we multiply 25 by 7, we will get 175. And 175 is exactly 30 more than 36 times 4. So that gives us our full list of elements of G here. So G is equal to the following set, where we have 1, 7, 13, 19, 25, and lastly 31. Great, and you can check that that is a group of order 6. Awesome. So now let's go ahead and get into our next example. So for this next example, we just want to list 5 examples of groups of order 8. So I'm going to list them for you here, and if you want, you can do some research on your own to see that they are in fact groups of order 8, as some are more obvious than others. So the first most obvious example, in my opinion, is Z8, which is just the integers modulo 8. Our next example should also be familiar, and that is D4. Next, we have Z4 cross Z2. And then we have the quaternarians. I hope I said that right. And then for our last and fifth group, which is of order 8, we have Z2 cross Z2 cross Z2. Great. So that is 5 examples of groups of order 8. So now let's go ahead and get into our next problem. So for this problem, we want to suppose that G is a group such that for all A, B, C, D, and X in G, we have that if A times X times B is equal to C times X times D, then AB is equal to CD. And what we want to show is that G is abelian. So what we really have here is a group where we have this middle cancellation property. So we're going to use that to our benefit here to show that G is abelian quite easily. So we actually have a very, very simple setup here. And what we're going to do is we're going to suppose that we have B, which is an element of G. And then we want to consider the following. So all we're going to consider is that B is equal to itself, B. And we can rewrite that in the following way. So first, on the left, we are going to multiply by the identity element E. And just the same way, we are going to multiply on the right-hand side of this equation by the identity element E. Great. And this is totally fine because the identity element will not be changing our B here. And then now on the left, we're going to replace our identity element in the following way. We're going to replace it with A times A inverse. And then on the right, we are going to replace it with A inverse times A. And you can see that A inverse, and we can see that A times its inverse will obviously be the identity element. So really what we're doing here is making a clever substitution while still maintaining the fact that we're multiplying by the identity. So let's go ahead and make that substitution now. So on the left-hand side, we will have A times A inverse times B. And on the right-hand side, we will have B times A inverse times A. And now you can see we can apply our middle cancellation property, as we have A inverse is nestled in between both sides of this equation. So let's go ahead and cancel those out now. So once we cancel those out, we will have AB is equal to BA, which is exactly what we wanted to prove to show that G is abelian. Great. So let's go ahead and get into our final example now. So for this last example, we want to show that the group, which is the 2 by 2 matrix of one real number where A is not equal to 0, is a group under matrix multiplication. So to check that G is a group, we have 4 things to check. First, we have to check that it is closed under matrix multiplication, which is not necessarily obvious given that we have a restriction on the elements that we can have in our 2 by 2 matrices. And then we have to check that there is an identity, an inverse, and associativity. But fortunately for us, we don't actually have to check associativity because it is inherited from the operation of matrix multiplication. Great. So since we don't have to check associativity, let's start by checking closure. Great. So to check closure, what we're going to want to do is take 2 elements from our set G and show that if we multiply them, or rather use our binary operation on the 2 of them, that we will get something that is also in our set G. So what we're going to do that is we're going to suppose that we have 2 elements from our set G. Let's call one G, little g, and call the other one G prime, and they will be in our big G. And then we're going to let our G's equal the following. We will have little g is equal to the 2 by 2 matrix of just A's. And then we will have our G prime is equal to the 2 by 2 matrix of just B's. And then we need to add this condition on the end that A and B are both not equal to 0 in order for these to be properly elements of our group G. Great. So from here, what we want to do is we want to consider G times G prime. So we have G times G prime. Well, what's that going to be? Well, we can use our standard matrix multiplication rules here, but we're going to see that because each of the entries in both of these matrices is the same, that each of these entries will also be the same, because if we swivel our first row of G right here into our first column of B, what we're going to get is A times B plus A times B, which is just going to be 2AB. But that's just going to be the same for each individual entry in this matrix, so we'll have 2AB for all 4 of the entries here. Great. And since A and B are both non-zero, we can't multiply them together with 2 to get something that is equal to 0. So that means that G times G prime must be an element in G, and we have proven closure here. Great. So next, let's move on to proving the identity. So to prove the identity, what we want to show is that there is an element which is in G, such that when we multiply it by any other element in G, it will just return that element. So we're going to start with the exact same setup that we did before. What we're going to do is suppose that we have 2 elements which are in our set G. So we're going to suppose that we have a little g and then an I, which are in our big G here. Great. And just like before, we are going to let our G and I have values. So we're going to let our little g be equal to the set of all A's, just like we did before. And then we are going to let our little I just be equal to the set of all E's, because we want to find out what this E will be to be the identity. Great. And then we want to consider our G times I here. So we want to consider G times I. Well, when we multiply G by I, since we already did our closure, we know exactly what we're going to get from the resulting matrix, and that will be 2A times E for each entry here. Great. And so all we need to do to prove that there is an identity here is prove that we can plug in some value for E that will return us A for each of the values in this matrix. It's quite easy to see that we can let our E equal 1 over 2. And when we do that, we will have achieved the desired result. So if E is equal to 1 over 2, then G times I is equal to just the matrix of all A's, which means that our identity is going to be the matrix of all 1/2. So thus, the identity for our set G, so I'll go ahead and write that, for G is going to be equal to I, which is equal to the set of all entries being 1/2 in this 2 by 2 matrix here. Great. So now we've proven closure and identity, and like I said, associativity is inherited by the operation of matrix multiplication. So now all we have left to prove is that there exists a inverse for each element in G that is also in G. Great. So let's go ahead and get to that now. So like I said, we are going to be doing the inverse here. So to prove that there is an inverse, we're going to do exactly what we have been doing. We're going to take 2 elements. So we're going to suppose that G and, let's just say G prime again, are in our big G here. And then we're going to let them have the following values, where we have our little g is equal to the set of all A's here. And then we're going to let our big G be equal to, let's just say, all B's once more. Great. And then we want to consider, just as we have for each of these proofs here, we want to consider G times G prime. Well, like I said, we've already done this exact calculation before, so we can just write out what that's going to be, and that's going to be 2AB, 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 and 2AB. And what we want to find is a value for B that will just return the identity matrix, or 1/2 in this case. And it's pretty easy to see what that's going to be. So if we let our B here be equal to 1 over 4 times A, when we plug that value in for B, we will find that we have gotten exactly the identity. So if we let B equal 1 over 4A, we will have that G times G prime is equal to 1 over 2, 1 over 2, 1 over 2, and 1 over 2, which is exactly equal to the identity. So thus we have shown that G prime is actually equal to G inverse, and we have shown that for an arbitrary element, which we have as little g here, that we can find an inverse that is also in G. Great. Now that we've proved that this set is closed and that it has an identity and an inverse, and we also know by matrix multiplication that it is associative, we have proved that this G here will be a group under matrix multiplication. Great. So that finishes this last example off, and that's a good place to stop.